What are those? What's going on? Why do I need those? Let's head over to the steel manual and let's see what we got. See you in there. So here we are where we left off in Chapter J, and now we got to go on a journey together. We got to flip all the way through this goddamn book. You ready? Oh, we're here. Okay. Part 3. It's literally one page after. Block, shear, strength. Oh my god, we made it, everybody. Okay, so what do we got here? We have this equation down here, which you're like, oh, that doesn't look so great. But don't fret, it's actually not bad at all. You can see that it's just components of shear and tension and their respective areas based on the plate for one another. So you have this one right here is for shear. This one right here is for the tension portion of it. And they give an ultimatum that it has to be less, so you're using F sub U for rupture. That equation needs to be less than your yielding equations over here. So again, sorry this is drawing so large with this pen. PDF's having a tough time, but let's go in and use this equation and figure out what our block shear is. All right, see you back over there. So we know that Rn is going to equal 0.6, which is part of the equation, times F sub U, which we know is 58 KSI, times ANV, plus UBS. You're like, whoa, 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 what the heck is that? Hang on a second. UBS, we'll get it, times 58 KSI for FU again, times ANT. So we have a couple things we need to find. UBS, if we go back to the steel manual, it's actually talked about right here. So typical cases, or right above here. Where the tension stress is uniform, UBS equal to 1. Where the tension stress is non-uniform, UBS equal to 5. In the user note, they say typical cases where UBS should be taken equal to 0.5 are illustrated in the commentary. So there are sections back in the commentary where you can check that out. In the 14th edition, so again, the maroon one, this one that we're in right now is the 15th edition. I actually have it written out right here where that commentary page is. So in the 14th edition, it's 16.1-412. So you can go there. It's going to be very, very close in the 15th edition to that page. So I would suggest for the PE to jot that down in there, because that helps you flip over to that if you're not sure. For us, so what does that mean, uniform tension? Well, if we head back, uniform tension means along your tension plane, which is up top here. And all that means is that since we have one row of bolts, we are going to have tension pulling down on this piece of the plate right here and have tensile stresses. Those in this type of condition are uniform tensile stresses, which means that UBS equals 1.0. So that's easy. That just goes away because it's 1.0. So now we're just left with ANV and ANT. Well, ANV is just the area net for our shear zone. So our shear zone we have marked right here. What's actually happening is if we actually dashed that all the way through, going right through the center line of our holes, so we need to subtract out and just find what the meat is. So what distance between there, plus that, plus down here. That's all those added up is A and V. So what would I do? Well, first I know that the top here to the center line of the bolt is 1 1/4 inch, and we know that just from the problem up at the top. And that's to the center line of the bolt. So that's to right there, right in the center. So from that point further down, that would be 11.5 inches minus 1 1/4 inches, which equals 10.25 inches. We need to subtract, well, what would I do here? I would first say, what do we say above? 3/4 of an inch diameter plus 1/8 inch diameter for the full hole diameter of 0.875 inches. Well, we're already at the center point here at the top, so we need to subtract half of that. So minus 0.875 divided by 2 is 0.4375 inches. That gets us to the bottom of the first hole. And what you can do is just say each half hole is 0.4375 inches. And we have, I'm going to do this different color. I'm going to do it green. We have 1/2 of a hole to subtract. We have 1/2 of a hole, 2 of them here, and 2 of them here. That equals 1, 2, 3, 4, 5, 6, 7. So I would do 0.437 times 7, and I'd subtract that from 10.5. That would get us A and V equal to 7.4375 inches. And remember, it's not technically A and V yet. We need to multiply by the thickness of the plate, so times 1/4 inch, 1.859 inches squared. Whew, workout. Okay, so we have that, and now we need A and T. A and T is going to be a little bit easier. So same thing. A and T, we know that distance to the center point of the bolt hole at the top is 1.5 inches. And we know we just need to do 1.5 inches minus, we're going to go green again, just 1/2 of a bolt hole. We know 1/2 of a bolt hole is just 0.4375 inches. That is going to equal 1.0625 inches. Multiply that by 1/4 inch for the plate thickness. Gets you 0.265 inches squared. All right, now we have everything. So we'll plug back in to the top to get my beautiful face out of the way. Back into this equation. Oh, and phi, if we slap on phi, what's phi equal to? Phi is equal to 0.75, and that's in the steel manual. All that plugged in, phi Rn, going to be equal to 60 kips. But we're not quite done yet because we have an ultimatum, right? It needs to be less than or equal to the following equation. 0.6 times 36 KSI, so this one is Fy, it's your yield stress, times AGV plus UBS times 36 KSI times ANT. So UBS we know is 1.0, easy, that goes away. ANT we know is 0.265 inches squared. Awesome, that's known. Oops, quick mistake here. This is FU. It's 58 KSI, sorry. FU. So AGV, that is what we need to know. Well, AGV, if we go back to the top, it is the same thing as ANV, except you don't subtract out any of the bolt holes for this. So this is just the total area of steel for that block shear failure mode, which means that it's simply just 11.5 inches, the depth of the steel plate, minus 1.25 inch. That 1.25 inch being this right here. And then that would be times the thickness of your plate, which is 1/4 inch. That's going to equal 2.5625 inches squared. Plug that into the top. Well, what does that equation get us? That gets us, and this is 0.265 inches squared. Sorry, head's blocking it. So what does this equation get us? This one right here. That equals, and we have to throw in our phi of 0.75, 53 kips. So total equation equals 60 kips for the first part of the equation. Needs to be less than or equal to 53 kips. So that's no good, which means that we can't use 60 kips, which means that phi Rn for block shear equals 53 kips, which is still greater than Vu, so we're okay. So that's block shear checked, so we're good. Next, we're checking the fillet welds. So this is checking the welds that connect the shear tab to the wide flange column. If we go back up, we will see that we have right here a 3/16 fillet weld on each side of the plate, connecting that plate to the wide flange column. So what do we need? Well, phi RN is actually just going to be equal to 1.392 times D in 16ths times length. Well, D, we had 3/16, which means that D is just 3. That's the size of your weld. L, well, we know that if this is your steel column flange, that plate, and we're not showing the bolts from the other half of that steel plate, is 11.5 inches deep, and the fillet weld was all the way along the depth of that plate. So we know that the length of the fillet weld is 11.5 inches times 2, because there's 2 welds. There's one on each side, as denoted right here, of that plate. So L is going to be 11.5 times 2, which equals 23 inches. Phi RN is going to equal 96 kips, which is greater than VU, so we're okay. And let's just go quickly back into the steel manual to show you where that is. However, if you do want to see more in-depth about weld design, then I suggest going over to one of my previous videos that I will be linking above right here. So let's hop over to the steel manual just to show you where that section is. Here we are, page 8-8. This is in the weld tab. So for all of you, here it is right here. Here's my manual. This is the maroon one, 14th edition. You have on the side here, besides my pre-made tabs, you have the already created indented index tabs that come with this book, and you will actually go to the weld tab itself, and that is chapter 8, all about welds. And right down here you have this simplified, so technically the full equation is right here with phi and omega and D and your flux strength and all that kind of stuff, but they actually simplify it down into a simple LRFD equation and a simple AISC equation, and that's what we use. So 1.329 kips per inch times D times L. Again, I'm not going to go any further than that. If you'd like to see more, head over to that previous video that I was talking about. But wait until we finish this one up. Appreciate all you. Next, we're going to check bearing strength at bolt holes. Let's head over to the AISC steel manual. So here we are, chapter J in the back, page 16.1-136. And if we just scroll up just actually to the previous page, as you see in the title here, bearing and tear out strength at bolt holes. So this is section J 3.10, I believe. And what we need to determine is, if we go back up top here, the available strength, phi RN, or Rn over omega, at bolt holes shall be determined for the limit states of bearing and tear out as follows. And you have phi of 0.75, so that's good. We'll keep that in the memory bank. And then what follows is bearing with a couple conditions and tear out with a couple conditions. So for bearing, the two conditions are dependent upon if deformation is considered for your design. For our design, deformation is not considered. We're not worried about it. So that means we would be rolling with this one right here. When deformation at the bolt hole at service load is not a design consideration. And same thing for tear out down below, same condition. So both of these we're going to be taking. So R sub n equal to 3.0 D times T times FU for bearing, and then for tear out, R sub n is equal to 1.5 L sub C times T times FU. And if you scroll a little bit more, you're like, boy, that's a lot of figures there, or a lot of variables. What are they? They're all right below and defined. FU, we know. D is the nominal fastener diameter, so that's 3/4 of an inch. L sub c is the clear distance in the direction of the force between the edge of the hole and the edge of the adjacent hole or edge of the material. And then T is the thickness of the connected material, which is your plate. So that is pretty straightforward. Let's jump back and plug all that in. So phi is equal to 0.75. Deformation is not considered, which means we have, and the two equations can be written like this. So you can do R sub n is equal to 1.5 LC T FU needs to be less than or equal to 3.0 D times T times FU. So T is your thickness of plate, which is 1/4 inch. F sub U is 58 KSI. That's from our material of our plate. D is equal to 3/4 of an inch, and that is our bolt diameter. So now we just need L sub C. So L sub C, they said, is the distance parallel with the direction of the force. So we know that our force, let me do this and do that. This is just kind of a close-up here of the plate between the bolt, bottom of bolt, and the next adjacent bolt or edge of plate. So that's going to be here to here. That is L sub C. And that L sub C is for each individual bolt, because all of these bolts are bearing on that plate. And obviously I didn't draw all 4 bolts here, I just drew a zoom in of the kind of the 2 bolts. So if we zoom out a little bit and we have our 4 bolts, 2, 3, 4, we're going to have an L sub C right there, L sub C right there, L sub C right there, and an L sub C at the end. Well, we know that center on center of bolts is 3 inches, and if we subtract 1 whole bolt diameter, that would get us the space in between, which we know is 0.75 inches for the bolt diameter plus 1/8 of an inch for the tolerance. So that is going to equal 2.125 inches. We'll call that LC1. So that would be LC1, LC1, and LC1. But the bottom here, we know that the distance to the center of the bolt to the edge of the plate in this instance is 1 1/4 inch. And we need to subtract half of a bolt diameter because we're right here. So we just need to subtract out that little bit of it. So that's going to be 1.25 inches minus 0.75 inches plus 1/8 of an inch divided by 2, which is going to equal 0.8125 inches. And that we'll call LC2. So with all of that, let's plug in. So Rn equals 1.5, L sub C1, we'll call it. So 2.125 inches times 1/4 inch times 58 KSI. And for LC1, we know we have 3 conditions where that happens. So we're going to multiply that by 3. And then we're going to add the same thing, 1.5, except now we're using LC2, which is 0.8125 inches. Again, 1/4 inch, 58 KSI, and there's just one of them. That is going to equal 156.3 kips. But we need to compare that to this up above. So up above, it's going to equal 3.0 times 3/4 of an inch, the bolt, times thickness, 3/4, times 58 KSI. And this is just bearing for the bolt, whereas the other one was tear out. So for bearing, you have 4 bolts that are doing equal bearing in this case. That is going to equal 130.5 kips. So this is what is our controlling case, so the bearing, And then we got to slap on our phi for our final capacity. So phi Rn and phi equaling 0.75 is just 0.75 times 130.5, which is 97.9 kips, which is still really high. That's greater than VU. So we are okay. Looking good, team. But now we get to talk about the secret trick, the secret sauce to this freaking steel patty of excellence. And let's scroll back to the bottom. Well, what did we get to summarize? Well, we have, what's our controlling, our governing case here? Man, we did a lot here today. So bolt shear, 72 kips roughly. Okay, not bad. Yielding of the plate, 62.1 kips. All right, so that is now taking the lead. Rupture is 52.2 kips. Now that is taking the lead because that is our least capacity. So rupture of the plate. Block shear, we have 53 kips, so very close to rupture, but rupture still takes it for us. Fillet weld, 96 kips. That one's nowhere close, okay? So still rupture. Bearing at the bolt holes, we determine 130.5 kips. That's clearly not it either. That's kind of rare that happens, but. So rupture is our governing case here of the shear plate, we'll call it, shear tab. And phi Rn is equal to 52.2 kips. Well, do we need to check all of that criteria every single time we do this when we have typical shear connections? Because, I mean, you could go 4-bolt configuration. You can go a 6-bolt, you can go 10-bolt, you can go crazy with this. There's, depending on the demand that you need to satisfy, you could have something completely different. Is there any way to speed this up? Yeah, there is. So buckle in. Here we go. This is kind of the fun part. And it proves what I'm about to show you, proves what they did in order to derive these tables that we're about to go check out. So let's head over to the AISC Steel Manual. So here we are, Chapter 10. What is Chapter 10? Chapter 10 is the shear chapter towards the front of our steel manual, page 10-94. And what do we have here? We have tables, table 10-10A for single plate connections. Wow, we have that. And it talks about covering bolt, weld, and single plate available strengths in kips. That covers a wide range of different types of connections that you could have. And you just need to make sure that your connection falls under the criteria that they've tabulated. So let's check that out. Well, the plate is 36 KSI, yield strength, or yield stress. We know that. We're using 3/4 inch diameter bolts. Nice. N is the number of bolts that you have, 4 bolts. L is the length in the depth of your steel shear tab. We know ours is 11.5 inches, so that's good. Bolt group, group A, that's A325 bolts. I love it. This is looking pretty promising. Thread condition is type N, so the threads are within the shear plane. Hole type, STD, that stands for standard, so it's not a slotted connection. We just have a standard bolt hole. That's really awesome. And plate thickness, we know, is 1/4 inch, which there it is right there. So if we track all the way down, LRFD, 52.2 kips is the capacity of that type of connection. The exact connection that we have for this problem. Wow, go figure. Weird coincidence. And they have run through all the checks that we ran through, got the governing load case, or the controlling failure mode, and tabulated it here. And so they're saying that we have a total connection capacity of 52.2 kips. Let's go back and compare. Oh my gosh. It's identical. Phi Rn equals 52.2 kips per table 10-10A. And there you go. So when I talk about typical shear tab connections, that's where the industry has kind of gotten into a group of saying, hey, we know a wide range of accepted connections that have been tested through and through over the years, can be calced out perfectly by hand to prove that they work as well. Let's go ahead and expedite this a little bit, and let's create some tables that run through all those checks and give you your capacity of your connection. As long as you are in as long as you're in compliance with the design categories that we've chosen: bolt sizes, plate thicknesses, plate size, number of bolts, plate material, bolt material, slot conditions, or bolt hole conditions. So all of those different things that we needed to check our failure modes, they have compiled into that table for you. So they're helping you out. They're doing you a solid. The AISC Steel Manual, once again, the freaking holy biblical text, is doing us a huge favor all the time. I know it's big. I know it's scary. I know they're these little tissue paper thin pages that make you cringe when you first get this book when you're in college. But there's a lot of hidden tables in here that save you so much goddamn time. It's unbelievable. So have faith. They're trying to help you out. But you also need to know so that you can prove to yourself that you understand how to use these tables. And that is it for today. Like and subscribe if you haven't. Go on that mission and tell that one friend, whether you're in school, you're in your job, and you're like, man, this is making me so much better, or you're out there grinding, studying for your PE, tell a fellow study mate about this channel so that you can help them out. They'll help you out in the future. You're both helped out. You're helping me out. That means the world to me. So let's keep having this channel grow, and I will see you all in the next one. This is Rich with Kestava. I'll see ya. Bye.